Okay, so I'm going to talk about Dalton's law now. All right, so here's what we're going to do. We're going to talk about 3 different gases with the same temperature but different pressures. Okay, so imagine I have 3 containers, but they're all the same volume, and I'm going to have a hard time drawing the same container 3 times in the same volume, but we're going to pretend that they all have the same volume, whatever that is. All these gases are at the same temperature, but I'm going to have different pressures. Now, let's look at the ideal gas law. PV equals nRT. One important thing I want to point out about the ideal gas law is where in here do I put what the identity of the gas is? And hopefully your answer was nowhere, because the ideal gas law works for all gases. It doesn't differentiate. All gas functions basically the same because the gas particles are bouncing around with a kinetic energy defined by their temperature. So it doesn't matter how massive they are, the kinetic energy is what's defined by the temperature. They don't really interact with each other because they're just bouncing loosely around. And there's so much space that the size of the particles doesn't matter. So every gas behaves exactly the same, all according to the ideal gas law. Now, it's called the ideal gas law because we're making some assumptions, but gases at normal, that we'll encounter in normal real life, adhere to this pretty closely. There's only minor deviations. So let's think about, I said that they have the same pressure and the same temperature, the same temperature and same volume, but different pressures. So let's take a look at this. Let's isolate what we can. So pressure is nRT over V. Okay, so if they all have the same volume, and they all have the same temperature, and R is a constant, it's always the same value, what's the only thing that is making these different gases have different pressures? Right? The answer is there's different numbers of moles. There's different amounts of them. So sort of the corollary we can come up with here is at a given pressure, at a given volume and temperature, the pressure is directly related to the moles of the gas. And that's really it. So imagine if I now took these 3 gases. So I'm going to define this as P1, P2, and P3. And they're really only based on the difference between N1, N2, and N3, right? What if I took all of these gases and put them in one of these containers at the same temperature? Now all of these gases are going to hang out together, right? The same amount of gas I had is what I'm trying to draw, but, right? So they're all going to exist in this one container that has the same volume and the same temperature as the individuals here. Well, the pressure is only going to depend on not what the gases are, but how many moles there are, right? So I'm going to take N1 plus N2 plus N3, right, over, times RT over V. Well, what this really is, I could break this up into, right, P total equals N1 RT over V plus N2 RT over V plus N3 RT over V. And what this really is, this is just P1 plus P2 plus P3. So what I'm getting at is that because of the nature of what's going on here, the pressure at a given temperature, all particles have the same kinetic energy. It's just a certain number of particles collide with the wall with the given energy. So the total pressure of a combined gas is just the sum of these 3 pressures. These pressures, P1, P2, P3, are what we call partial pressures. So the partial pressure of something is the pressure an individual gas in a mixture would exert if it were by itself. So, and Dalton's law of partial pressure says the total pressure exerted by a mixture of gases is just the sum of the partial pressures. So, what I'm really driving at is that oxygen is about 21% of air. I might be off by a little bit. And let's assume that 21, and I think that's by mass, but let's just kind of go with me on this journey. Let's assume that 21% of a mixture of the molecules in the air were oxygen. Well, that would mean that 21% of the pressure is being exerted by oxygen, right? So if I had a mixture of gas that was 60% N2 and 30% H2 and 10% O2, then not only are these the percentages of the gas, but they are also the percentages of the pressures contributed by the gas, and they always add up to 100%. So, if I had a sample of air collected when the atmospheric pressure is 742 torr, the partial pressure of N and O2 are given here, and water vapor is the only other gas. What's the partial pressure of the water vapor? Well, simply put, I would take 142 torr and subtract out the other two, because the total pressure, 142 torr, is just the sum of all three of these. So I get I keep saying 142, 742 minus 581 minus 141, and I get 20 torr is my pressure of the water. So Dalton's law of partial pressures it ends up leading up to some kind of cool things, but it itself is very simple. If you have a mixture of gases, the total pressure of the gas is the sum of the partial pressures. I think what's more important out of this, for moving on, is understanding what I mean when I say partial pressure. Partial pressure is the pressure exerted by that component of the mixture, right? It's contributing a certain amount of the pressure. So I think the idea of what a partial pressure is more important than understanding this summative law.